Hey everyone, so today let's discuss about matrix. So the last video we saw what vectors really are, and to build upon that, let's discuss matrix. So if vectors represent individual pieces of data, then matrices represent the entire worlds of data. Your dataset, probably a matrix. Your image, that's a matrix. Neural network computations, matrices everywhere. So the real question is, why does machine learning loves matrices so much? So what exactly is a matrix? So matrix represent linear equations and functions. Linear equations and functions. Suppose we have m and n, which both belong to natural number n, the set. Then m dot n will be a tuple of elements aij. So m dot n will be a tuple of elements aij. So aij represents one element of the matrix in which I goes from 1 till m and j goes from 1 till n. Now these aij elements, each aij element is ordered in a rectangular scheme of m rows and n columns. So if I have this rectangle, it will have m rows and n columns. So this is called rows, these are called rows, and these things are called columns. So according to that, it will be m and this will be n, m rows and n columns. Now this form, suppose I write any vector a equals to a11, a12 till a1n, and a21, a31 till am1, amn. Now this form is called as row column vector, in which every element aij belongs to real number r. Now coming to matrix addition. So matrix addition is very simple. It's just element wise, and like if I give you an example, a plus b, in which it will be a11 plus b11, a12 plus b12 till a1n plus b1n, and similarly am1 plus bm1 till amn plus bmn. It's like that. Okay, so each element of a and b matrix is added. So in this, so a was a11, as I showed you earlier, this was a, and b was b11, b12, b1n, bm1, bmn. This was the b matrix. So this gets added to this gets added to this gets added to this. So all this additions were taking place element wise. Now coming to matrix multiplication. So matrix multiplication. So matrix multiplication is not element wise, which means that Cij is not equal to Aij into Bij, but we can do element wise multiplication in programming, which is called as Hadamard product. So you can check on this on your own, what exactly is this and how is it calculated through programming. But today what I'm going to talk about is the normal matrix multiplication that we generally do, in which suppose I have three matrices A, B and C, in which A belongs to R m cross n, B belongs to R n cross k, and C belongs to R m cross k. So this is what I told you about in the previous video, that it's a m cross n dimensional space in which I have m list of rows and n columns of n list of rows and n list of columns. Okay, so suppose R3, then it will be as 1 2 3. Suppose R3 comma 3 cross 2, it will be 1 2 3, and suppose 4 5 6. So 3 rows 2 columns. Okay, this is my R. So R m cross n space dimensions. So coming back to the multiplication, so in this, the C is the resultant of A cross B. So C equals to A dot B, in which I can represent each element of C as Cij equals to summation of Ail and Blj, in which L will be from 1 to n, and I will be from 1 till m, and j will be from 1 till k. So to explain this even more clearer way, and to give you intuition about this, um, I'll again write my two matrix A11, A12, A13, A1n, A21, A22, A23, A2n, AM1, AM2, AMN. Similarly, B11, B12, B1n, B21, B22, B2, BM, B21, BM1, BMN. Now, if I have to find Cij, suppose I have to find C23, how I can find this? Okay, so it's very basic, the dimensional multiplication knowledge that we have from our basic school level mathematics, that suppose a cross, sorry, a m cross n and b n cross k, this can be multiplied because m and n are same. But if a m cross n and b l cross k is there, this cannot be multiplied because this needs to be same. So I have a and b. So to bring 2 and 3 here, what can I do? I need a is 2 and any value x, and I need b is x and any value 3. Sorry, x and the 3. So anything multiplied will always be giving me as C23. So if I see A2x, A2x is basically this thing because I have 21, 22, 23, so 2x, and bx3 will be my this column, b13, b23 will be m3, this column, because bx3, so 1 3 2 3 3 3, so this will be it. So why we are saying that I is from 1 to m? Because we are treating as this I, and this will be j. So I is from the a, and a we are going from 1 to m. See this, we are going from 1 to m, so there are m rows. That's why we have written that I goes from 1 to m. Similarly, j, why j goes from 1 till k? Because this is our j, I comma j. So j means b means this thing, these things are our p's, which goes from 1 till k. So this is actually b, k, this is k. Okay, so this goes from 1 till k. And why this is it, I've given you because of the dimensionality rule. Okay, so instead of that, I just, it's there, we can also write it as x. So x till 1 to n. Okay, yeah. So this is called as the dot product. This is called as a dot product. Now there is one rule that a dot b is not always equal to b dot a. That is, it's not commutative. Now coming to the identity matrix. Suppose if I take any r of n cross n, then my identity matrix will be 1 1 1 1, means all the diagonals will have 1 and rest all values will be 0. Okay, this is what my identity matrix is. Suppose my suppose if I write I3, which is basically r 3 cross 3, because identity matrix are generally square matrix, so it will be 1 1 1 0 0 0 0 0 0. All diagonals have 1 and rest all the values are zeros. So this belongs to r n cross n. So in this we have several properties. I mean, not in the identity matrix particularly, it's rather like as a whole the matrix, because I have associative, I have distributive, and I have the identity property. So what is the associative property? So I have three matrix. So for all ABC, in which A belongs to R m cross n, B belongs to R n cross P, and C belongs to R P cross Q. So in this, ABC equals to ABC. You can check the dimensionality also. Suppose A is m cross n, B is n cross P, so the resultant will be m cross P. And what is C? P cross Q. So this will be m cross Q. Fine. And BC resultant will be n cross Q, A is m cross n, it will be n cross q, hence we'll get m cross q as well. So dimensionality is working pretty well, and you can see by putting values also if you really want to test this. Then distributive for all a comma b which belongs to r m cross n, for all c comma d which belongs to r n cross p, we can write a plus b c equals to ac plus bc and ac plus d as ac plus ad. Okay, so you can also check them through putting values or even the dimensionality. Now identity property is that for all a which belongs to r m cross n, I m a equals to a, equals to a. So I have written I m and I n here because, as you know, a belongs to m cross n. So if this is I m, that means it's m cross m identity matrix, and a is m cross n, so they can be multiplied, giving us m cross n final product. And in this a is m cross n, that's why we are taking n cross n to make it equal to, to get the value of a. That is the identity matrix. So any matrix multiplied by the identity matrix, that's that matrix itself. Now coming to let's talk about transpose now. So if I have two matrix A which belongs to r n cross n and B which belongs to r n cross m, my B I j will be equal to A j I. And so if this condition is met, then I can say that B is transpose of A, or A is transpose of B, whatever we can call that. So what exactly transpose is that we have a matrix, suppose 1 2 3 4 5 6. Now if I do its transpose, it will become 1 4 2 5 3 6. So the row I had, I converted it into a column, right? And the column I had, it became my row. So rows and columns are interchanged. So that's what happens in transpose. Simple. So aij, suppose I'll show you how. So this was my a11, a12, a13, a21, a22, a23. So this will be b11, b12, b21, b22, and b31, b32, right? So if I check this in everything, so b11 should be equal to a11, yes it is 11. b12 should be equal to a21. What is a21? 4. So 4 and 4 checks it out. Then b21 should be equal to a12, 22. b22 should be equal to a22, 5, right? b31 should be equal to a13, yeah, and b32 should be equal to a23, 6. So yeah, this works out pretty well. Now let's come to inverse. It's quite tricky, but yeah, it is easy, very easy. So I have a matrix of R, suppose m cross n, and I have B of n cross n. Now if AB equals to my identity matrix and equals to BA, then we can call that A is inverse of B, or B is inverse of A, vice versa. This also goes pretty well, and we can denote it as this, or A equals to B inverse. Both work. So one more thing to note is that not all the matrix have their inverses. Okay, so like speaking in simple terms, any matrix which we multiply to a given matrix so that we can get an identity matrix, that matrix is called the inverse of the other matrix. If I tell you, like this will look upon on further videos, that the formula of inverse is like adjoint of matrix A divided by the determinant of matrix A. So in this, if the det is 0 of a certain matrix, its inverse won't exist, right? Because we cannot make denominator 0. So only those matrix whose det or determinant is non-zero, only for those inverse exists and not for all. So if inverse exists for a matrix, then we call that matrix as singular or non-invertible, And if the inverse does not exist, then we call it as regular, invertible, or non-singular, So let me give you an example here. I have two matrices A11, A12, A21, A22, and it belongs to R2 cross 2 as we can see, and we have B as A22, A11, A12, and minus A21. Now to check whether B is inverse of A or A is inverse of B, we will multiply these two and check whether or not we are getting the identity matrix. So I'll just multiply both, and A dot B I will get as yeah, so this is what I get as A cross B. So I can also write this as A dot B equals to A11, A21, and 1001, since I can take this as common and bring it out for multiplication, the general multiplication rule. So this is my identity matrix. I can write it as I. Now what I can do is multiply A inverse on both the sides. So what I will get is A inverse A B equals to, since this is scalar quantity, I can move it. If we have vectors, we cannot move it like that. So A11, A22 minus A12, A21, A inverse I. So anything multiplied by with I stays the same. So this will be A inverse. Anything multiplied by its inverse will become I, and again anything multiplied by I is same. So it will be B. So what we get is B equals to A11. Okay, and let's shift also. So I get as B. This is A minus A. Sorry, A inverse. And if I bring it to LHS, I will get that in the denominator. So it will be B divided by A11, A22 minus A12, A21 equals to A inverse. This is what I get. Now one thing that we have to remember is that denominator cannot be 0. Hence we'll put the condition of not equal to 0. The A11, A22 minus A12, A21 should not be equal to 0. So A11, A22 should not be equal to A12, A21, which is also comes from the determinant part, as I told you. So this is basically the determinant. This part is basically determinant of the matrix A. Okay, so this should not be equal to 0, which I also proved it through the calculations. Now you can further check by adding the numbers and verifying by taking a few examples, because you need to practice this if you really want to learn the maths, right? Because without practice we cannot master anything. So with respect to that, let me give you an example which you can work on. I'll give you two matrices A 1 4 4 5 6 7 7, and B I'll give you -7 -7 6 2 1 -1 and 4 5 -4. Now check whether are they inverse of each other. So check whether B is inverse of A or not. Okay, it should be pretty simple, and it will be a good practice. So few more properties for the inverse and transpose. First, A inverse equals to same. So this I explained you why it happens and how it happens. Second, so all these properties you can verify by putting numbers or working through examples, or even checking online that what exactly is the proof. I won't be delving in the algebraic proof that much because it won't be required here. So it's just many people think that matrix can be thought of as normal algebraic calculations, like A plus B inverse can be A inverse plus B inverse, right? But this is not true. As you can see, this is not true. So they have some different calculations and different methods of working. That's why we need to remember these properties, because it really helps in calculations also. Fifth is A plus B transpose equals to A plus B transpose, and sixth is A B transpose equals to B transpose A transpose. And let me remind you that this thing is not equal to A transpose B transpose. Now coming to the symmetric matrix. So what exactly is symmetric matrix? I have A which belongs to R n cross n, and it will be symmetric if and only if I have A equals to A transpose. This is the condition. So for symmetric, I have the condition A should be equal to A transpose, and for inverse, A dot B should be equal to I. So you have to remember these conditions. So for symmetric matrix, A should be equal to its transpose. So in this, the R, as you can see, is n cross n. It's a square matrix. Square matrix. Why we are calling it square matrix? Because n and n, it has equal number of rows and equal number of columns. So the sum of symmetric matrix remains symmetric, but the product of symmetric matrix may or may not be symmetric. So let me give you an example of symmetric matrix. Any matrix in which A is equal to its transpose. So identity matrix is symmetric because see 1 1 0 0. If I do its transpose, I'll get is this only, right? So this is symmetric. Other symmetric examples, if I give you, can be 1 2 2 3 3 1 1 5 5. Yeah, make it 5. So this is one more symmetric matrix. Then let's see what happens when we multiply a matrix by scalar. Let's see what happens. So I have a lambda, which is a scalar quantity which scales element of A. Suppose if this is my this, and if I multiply by lambda, it will become this. This is my normal A and this is my lambda A. Okay, think of lambda as a scaling factor. So lambda belongs to R. Then I have A, which belongs to R m cross n. Then lambda A, I'll call it as K, and Kij means any element of the matrix K will be equal to lambda A, or you can say lambda Aij. To show this, if I have A as 1 2 3 4, lambda as 2, the K that I'll get is 2 4 6 8, and Kij. So suppose K12 equals to 2 into A12. What was my A12? 2, and 2 into 2 is 4. So that's how multiplication through scalar occurs. Now again, a few properties. If you keep practicing, you'll just learn these properties by yourself. There's no need to learn this specifically. It's just based on practice. So I have lambda and phi, which belongs to R. Then lambda phi c equals to lambda phi c, in which c belongs to R m cross n. So sorry, this is the first thing, and this is the associative property. Second is let's see what happens with the transpose. So this equals to C transpose lambda transpose, and lambda transpose is basically lambda itself because it's scalar. So Ct lambda, or we can also call it as lambda Ct. Then you can also write as lambda Bc equals to lambda B. Again, the associative property. Lambda, since it's lambda, right, it can be multiplied in any way. So this BC should be remain same. It cannot be CB, otherwise the answer will come wrong. The BC order should be maintained. Lambda you can multiply anywhere to any matrix because it won't matter. Now the distributive property is lambda plus phi. That's C equals to lambda C plus C. Lambda B plus C will get as lambda B plus lambda C. Again, you can take few examples of them and check, verify. This is the best thing if you want to check any theorem or any formula, that just put examples in them and you'll automatically know, yeah, this works or it doesn't. Next is the compact representation of systems. So this I talked about the previous videos, that if we have lots of equations, lots of variables, how can we express those? And I told you that we can express those through matrix and vectors. We have various vectors, so assemble all those vectors in a matrix and there you go. So if I have all the coefficients, if I bring all the coefficients in one place, call it a matrix A. If I bring all the variables in one place, call it matrix X, and all the RHS values, and call it a B. So here I will get A dot X equals B. So this is basically the compact representations of systems. So now talking about the ML connection part of this matrix. Suppose in my data I have three things: age, salary, and spend. Let me take its values as 23, 31, and 19. Salary is 50k, then 80k, 20k, and expenditure is 1200, 3000, and 500. So this is the data that I have. Now here's when machine learning enters. Imagine customer data. Each row belongs to one particular customer, and each column is a feature. So this is feature age, feature salary, feature spend, expenditure. Mathematically it's a matrix. We can write it as 23, 50,000, 1200, then I have 31, 80,000, 3000, 19, 20,000, and 500. So this is a matrix, and this is why ML love matrices, because datasets naturally fit the structure. Anything we can, any data we have numbers, we can write it in this format. So why this matters for ML? I mean, why study all these matrices and all? So this isn't some random math torture. Matrix multiplication lets machine learning transform data very efficiently. Say I have input data cross weights, and I'll get the output. We'll talk about what is input data, what is weights, and what is output. We'll talk all that later. It's just the basic machine learning. What happens in that? I'm just relating how is it important and how is it working there. So if you see, it's of the form AXB that we just saw, right? So it is somewhat relating to what we just studied. Now in machine learning, we have neural networks. Neural networks have matrices everywhere, linear regression everywhere, transformations everywhere. You cannot escape from matrices and vectors. I mean, this is the most fundamental part of machine learning. So I think so I answered that. Why does machine learning love matrices? We have datasets, transformations, then we have neural networks and efficient computations. These are the reasons why machine learning loves matrices, because matrices let us represent massive structured data and transform it efficiently using mathematics. Now, vectors gave us individual data points. Matrices gave us the entire data sets. Next, things get even more interesting, because soon we'll talk about systems of equations, transformations, and the math that powers the actual ML models that we use. So, thank you.